Good evening, everybody. Welcome to Slooh. This is Paige Godfrey here, and if you're listening, you are tuning in to my Intro to Astro crash course. This week, we are going to talk about fast radio bursts and other weird signals that seem to come from space. If they have explained sources, if they don't have explained sources, and we'll go through what these different signals mean and how we detect them. So if you're following along with me on Slooh.com, I will be screen sharing as usual, and you want to tune in on Slooh.com, that way you can see what I'm sharing with you. Tonight we have what are artist renditions of some of these sources, of course, because to us they just look like white points of light when they're so far away that they're sending these really, really obscure signals, but we'll get to that in a bit. So here's my screen. I am currently on Slooh.com, actually looking at the Chile telescope, the Chile Wide Field, right now. And if you were online earlier today, you got to see the solar scope was back online, finally! So we've had some major snow and ice storms in the Canary Islands over the past few weeks. And what happens is all this ice builds up around the domes, and then the dome shutters can't open. And this was obviously a problem, and manually, you have to go out manually and like chip the ice away. But every time they would go out to chip the ice away, more ice would come, more snow. So finally, the solar scope was online today, and so that's good news for the rest of the scopes, that hopefully they'll get chipped away soon and be back online. In the meantime, we can ponder fast radio bursts and other weird signals coming from space. So when we think about signals that come from space, we don't usually think of aliens, right? Or maybe we do, but scientists usually don't. We think of predictability. We think of things like pulsars, which are the leftover remnant core of a dead star, that as it's spinning, it's beaming a light out. And like a lighthouse, if the beam hits us every time it goes around, because we're in that field of direction, that's a predictable source that happens every couple milliseconds or so, and we expect it to repeat, and it does repeat. There's a constant radio flux of a magnetic field around a star, or the high energy ultraviolet and gamma rays that come from a supernova explosion. We look out in the sky, we see these signals, and we know what they are. They have patterns of repeatability, timing patterns, well-defined compositions and structures. We get the light curves. We know what we're looking for, so we know what we're looking at. But what happens when we don't know what we're looking for, and so we don't know what we're looking at? Back in 2007, an astronomer named Duncan Lorimer discovered a brief, very strong radio signal that was coming from a source in space that he could not identify. Sometimes weird signals like this turn out to, and usually, I should say that usually weird signals like this turn out to just be glitches, whether it's in the telescope equipment or interference from communications equipment around Earth, weather, anything that, anything that something could even pass by in space that would give you a really odd signal. But those also can be ruled out. It's easy to determine if the source was from Earth or from outer space, and whether it was the telescope equipment or not. But this signal that Lorimer discovered was not Earth-caused. It was definitely extragalactic, and in fact, it came from over 3 billion light years away. So it was definitely not an artifact of Earth. Oh, I'm looking at our, I got distracted by the Chile scope, and it's like zoomed. There we go. Oh, it's just my computer being weird. If you've heard me complain before, my computer gets like really hot and the fan blows really hard when I try to do these streamings, but it's okay. Anyway, weird signals coming out of my brain. So this signal was extragalactic. It came from 3 billion light years away. Since then, about 24 more of these weird signals have been found, and they're so short and bright and in the radio portion of the electromagnetic spectrum that they're called fast radio bursts, or for shorthand, FRBs. And when we say fast radio bursts, we mean that FRBs last just a few milliseconds. They're super, super quick. And so far, we've only been able to detect them from Earth by pointing telescopes in exactly the right direction at precisely the right time. But since we don't know what we're looking for, we don't know where to point the telescopes and at what time to do so because we don't know where we expect them to be coming from. Okay, so what gives? Well, there's several theories to what FRBs could be. One option is that they come from collapsing neutron stars. Here is a depiction of a neutron star. So this is also what a pulsar looks like. Just for your reference, a pulsar is a neutron star. When a star goes through its lifetime and finally ends its life in a supernova explosion, the outer layers are blown off in a massive shockwave that permeates space, and what's left over is a really hot, dense core of gas from the star. It's called a neutron star. It's very small and dense, rapidly spinning, and if the magnetic field lines produce radiation beams that come off the poles. If you're following my mouse, these are the poles of the magnetic field lines. So the radiation beams come out of the poles. If the neutron star is spinning so that the radiation beams hit Earth and we detect it, we call it a pulsar. So a pulsar is a neutron star, but not all neutron stars are pulsars. And I just got way off topic, but that's okay because I think that's an important thing to know. So when we have neutron stars that are rapidly spinning, if they're spinning very quickly and have ridiculously dense cores left over after certain stars go supernova, they can collapse. If the neutron star is dense enough, it'll be overcome by its own gravity and it'll collapse into a black hole. But if it's spinning fast enough, it'll kind of like hold off that collapse for a little bit. And when the neutron star eventually is just about to collapse, right like that millisecond before, its magnetic field is going to be ripped apart, which could cause all the charged particles within the star to shoot out a quick, bright burst of radio waves. Maybe our fast radio burst. But see, things like this, and so I'll just disclaimer here, and I'll probably make a lot of disclaimers throughout all of this because I'm certainly not suggesting that any of these are aliens, but things like this haven't been detected. So this is why they're theories. They haven't been proven. So another possibility is that fast radio bursts come from two very dense objects merging, like two black holes or two neutron stars. As they spiral in towards one another, the merger causes a ton of energy to be thrown out of the system, possibly in the form of a fast radio burst. But these explanations only fit a single isolated fast radio burst, meaning that either the merger of two very dense objects or the collapse of a really dense neutron star, once it happens, it's done. And so you'll only get one fast radio burst. And up until 2016, okay, great, one fast radio burst, they're explained. However, in 2016, astronomers actually discovered 10 repeating bursts that all seemed to come from the same source. So how can we explain? We can't explain that the neutron star collapsed 10 times or that there were 10 neutron stars in the same RA and DEC part of our sky. These might have come from what we call a magnetar, which is a special type of neutron star that's extra magnetic and spins extra fast. These neutron stars might produce fast radio bursts when they send out flares. So the way we're looking at this neutron star here, and it sends out these radiation beams, if it was super, super, super magnetic, really strong magnetic field and spinning really quickly, the magnetic activity would be much stronger. And so it could send out really strong, fast radio bursts. But in order to detect these in the future, and to try to discover their sources, we need telescopes that cover large areas of the sky, but that are actually really insensitive because FRBs are so bright. And so we don't want super sensitive telescopes because they're going to be oversaturated. So based on the number of bursts we've found compared to how long we've spent looking for them in different parts of the sky, researchers think that actually an FRB might reach Earth as often as every 10 seconds. Think about that. Every 10 seconds, there might be an FRB. But we just don't see them because we don't know where to look and when to look for them. They only occur over a millisecond or so. How could we possibly see them if we're not looking at precisely the right point? Thoughts to ponder. Here is an image of a telescope that's actually, it might be coming online soon. I haven't followed up with it specifically, but it's called CHIME, and it is like a very wide large array telescope that is insensitive that would be able to detect these, and that's what it's being built for. It's supposed to be coming online at the end of last year, at the end of 2017, so I'm not sure if it has actually. That'll be interesting to follow up with. So those are fast radio bursts. They are not, though, while they are probably one of the hottest weird signals in space right now, they're not the only weird signals. The next one we're going to talk about actually comes from a star, and actually instead of it being like a strong signal, it's actually a weak signal that confused astronomers. So this is called Tabby's star. Its nickname, of course, the star has a regular like designation with a bunch of numbers after it that, just confuses everybody. But this is also known as Tabby's star. It's also known as the WTF star. Where's the flux? In 2015, astronomers discovered a signal from a star that was strange because it was actually less signal than they were expecting it to be. So it got denoted, where's the flux? When we look at a star, the light that comes in, the photons that we count, we call it flux. And so that's why where's the flux came from, which I think would make really awesome t-shirts. But this star is missing a large portion of its flux. Up to a record 22% it's been recorded. This is seen as a dip in the light curve that comes from the star, and these dips last on the order of days. So let me go show you what this light curve, I poked back to the site so you could just see what the telescope was looking at. It's looking at the Crab Nebula, and I bet you want to pay attention to this because it's actually going to turn beautiful colors in a minute or two. So definitely get your camera trigger button ready. Oh, I just took a grayscale picture by accident. It's okay. So this is Tabby star. This is the image of it in the sky. And if we shoot over, we can see these are the dips that I'm referring to. So we have our constant flux coming in from the star, and every so often we get a huge dip in flux. And now, normally, an astronomer would look at this and say, that's not real. That's an artifact, a glitch in the system. That is not a real feature. But in fact, for this star, it is a real feature. This is where we're missing the flux. What on earth is blocking that light from reaching us? The media, and admittedly some scientists, but most definitely the media, jumped on the alien bandwagon to explain this in the beginning. They probably still do. But alien megastructures like the Dyson sphere were the the big go-to. So Dyson sphere, if you've ever heard of the Kardashev scale, it's a scale that describes the capability of a civilization, the advancement. So a civilization grows really large and becomes more and more advanced, and its energy demands increase because the population grows and we have all this technology. So the Kardashev scale is a way to measure the civilization's technological advancement based on how much usable energy it has at its disposal. So there's different levels, and I'll start off by telling you that we on Earth are a low type 0 civilization because all of our energy only comes from our Earth, from our dead plants and animals here on Earth. We don't harness energy. Well, we have solar panels, and so we're moving towards this, but the next level, the first type 1 level, is given to a civilization who's been able to harness all the energy that's available from their star, gathering it and storing it to meet the energy demands of their growing population. So yeah, we have solar panels, but we certainly haven't harnessed nearly any really to scale of the energy of the sun to be a type 1 designated on the Kardashev scale. The next step is a type 2 civilization, which can harness the power of their entire star. So not merely transforming starlight into energy, but actually controlling the star. So one of the methods for this that's been proposed is the Dyson sphere. It's a device or a thing that would encompass every single inch of the star, like a big sphere around the star, gathering all of its energy output and transferring it to the planet for later use. And then the scale goes on and on. blah, 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 to type 5. Type 5, I'll just, for kicks, I'll tell you. This is like gods having the knowledge to manipulate the universe. So I'm not suggesting that the Kardashev scale is anything legitimate to go off of, because we certainly, we're the only living human civilization that we know of. But, this is where the Dyson sphere has come from. So maybe there's this Dyson sphere covering Tabby's star, and so we see the dips where it's the light being stolen from the Dyson sphere. But astronomers have also hypothesized several scenarios that are physical science for why the star's light was blocked. And some of them are multiple planets that are going around, or an asteroid belt, or dusty comet fragments that are orbiting the star. But actually, none of these really even work. So Tabby's star is an F-class star. So if you know the spectral type classification, it starts with O, which is the hottest star, and it goes O, B, A, F, G, K, M, where M is the coolest type star. And our sun is a G star. So Tabby's star is an F star, which is a bit bigger and hotter than our sun and brighter. It's Tabby's star is about 1,500 light years away, and it's in the constellation Cygnus, if anybody wants to go looking for it. It was one of the 150,000 stars that the Kepler Space Telescope was staring at for 4 years, starting back in 2009, to try to find planets around other stars, called exoplanets. So the reason that so Tabby's star could have planets. We're not saying it doesn't. However, it's since Tabby's star is probably more than 2 million kilometers in diameter, it's about 50% larger than our sun. So imagine a planet like the size of Jupiter around it. It's barely going to cause a dip in this flux, in this brightness, a few percent at most, nothing near the 22% dip in brightness. So whatever has passed in front of Tabby's star that blocked this light was big, the size of like a small binary star. And yet we haven't seen one. There is no binary star in evidence. So the newest data is showing that the different colors of light that are coming from Tabby's star are being blocked at different intensities. So whatever's passing between us and the star is not just like this opaque alien megastructure, as would be expected from also like a planet or like, like a terrestrial planet that is just blocking all of the light with no preference to color. But it could be circumstellar material like exocomets or dust, which seems to be the favoring idea right now, that is blocking the star. It's nothing like majorly huge, but a bunch of really small things that are like maybe going around in clumps. There are some astronomers that are also favoring the idea that nothing's blocking the star, that it's getting dimmer on its own. There's some weird intrinsic physical process happening that's consistent with the latest data, but we don't have a theoretical physical model for this as of yet, at least that I'm aware of. So that's another weird or lacking of signal coming from space. So now let's pop back. Oh, here was I just pulled this up because this was one of the like comet theories going around the star. That was a nice image. Let's travel back in time a little bit now to some weird signals from the past that have never been explained. You might be familiar with the WOW signal. It's a strong, narrow band radio signal. So narrow band meaning that it comes in really sharp at a narrow wavelength range instead of a wide wavelength range like, let me go back. Well, this is in time, not wavelength, but this is in wavelength. So if you're looking at this graph with me, this peak here is spanning about 20-25 microns. So a narrow wavelength radio band is what we're talking about here. Really narrow, like much more narrow than this. So this signal came in 1977 by Ohio State University's Big Ear radio telescope. This telescope was a SETI telescope. So SETI stands for the Search for Extraterrestrial Intelligence. So this was one of the SETI telescopes that the signal came from, and it appeared to come from the constellation Sagittarius, and it seemed to have the hallmarks of an extraterrestrial origin. Astronomer Jerry Eman discovered this a few days after the signal came in while he was reviewing the data, and he was the one that wrote on the computer printout, "Wow," on the side, which is how the signal got its name. The entire signal lasted for 72 seconds, but has not been detected ever again. So there's been several subsequent attempts by Eman and others. I think Eman said that they tried like 50 times to find it. Many hypotheses on where this emission came from. Natural, man-made, did it come from Earth? Did it come from space? Definitely came from space. But the WOW signal is the strongest candidate for an alien radio transmission, probably, because it has not been reproduced and it has not been explained. And lastly, so Carl Sagan is very, very famous and very famous in this field. Back in 1980, he started the Planetary Society, and he's been involved in a lot of these SETI projects. And one of them was called META, or Mega Channel Extraterrestrial Assay. Of this telescope, each channel or sort of like station that it was tuned to, you can think of a telescope looking for radio frequencies, like the radio on your car. Like you tune to a frequency, you tune to a channel. So this telescope was tuned to a very exceptionally narrow frequency range. They did this because there is no known processes out in space that could generate such a sharp radio line. Remember this narrow band thing. If they picked up anything falling into such a narrow channel, then they assumed it must be from artificial intelligence and technology. So the META telescope is in Harvard, Massachusetts, and it's about 26 meters or 84 feet in diameter. It was online for 5 years of full-time searching and then 2 years of follow-up on the 5 years of data. Sagan reported that after removing the background noise and singling out specifically strong signals, out of the 60 trillion observations, that is a ton of observations, they were left with 11 signals, or they call them events, that have no explained source. So as he put it, and I'm quoting here, "They satisfy all but one of our criteria for a genuine alien signal. But the one failed criterion is supremely important: verifiability. We've never been able to find any of them again. We look back at that part of the sky 3 minutes later, and there's nothing. We look again the following day, nothing. Examine it a year later or 6 years later, and there's still nothing. Although none of these signals repeats, there's an additional fact about them that every time I think about it sends a chill down my spine. 8 of the 11 best candidate signals lie in or near the plane of the Milky Way galaxy." If you sit on that for a second, what Carl Sagan was saying is they can't report that these are extraterrestrial life, that it's artificial intelligence, that it's technology. You can't say any of that without having proof. All you can do is rule out what it's not, but you can't prove what it is without being able to verify that. But what intrigues him about this is to think that if they really were artificial intelligence signals, then 8 of them came from within our own Milky Way galaxy. It's a really interesting thing to think about, and there's a paper that one of my colleagues put out. It was a couple years ago now. I'll link to it when I post the summary from tonight. It was a really awesome paper. It was about cloaking the Earth and how we could use laser signals to either cloak the Earth and hide from extraterrestrial life, or send out signals into space, artificial signals that would alert another civilization that we were here. It was a short paper, but it was really, really cute, and I'll share that in the summary that I'm going to post after this. So let me just take a note to remember to do that. You might hear me typing. But yeah, so all of these signals, I mean, we can go all the way back to the 1970s to talk about weird signals that have still not been explained some, 30, 40 years later. But even still today, with the better technology that we have, instead of ruling out these weird signals, we're actually just finding more of them. I'm not saying we're finding multiple and multiple and they're all aliens, but we're finding different variety of weird signals. We have Tabby Star with the weird flux dips. We have fast radio bursts that come in single events, and then fast radio bursts that come in repeating events from the same source. And this is what keeps astronomers in the field. This is why we have funding and why we have jobs, because until something is explained, we want to try to explain it. So astronomers are working really hard to try to explain these weird signals, and there are a ton of physical science theories that will explain these. So we definitely don't need to jump to the alien conclusion, but until we can prove what it is, you are free to let your mind wander and to let your mind go, wow. All right, so I'll wrap up for tonight. Next week, we're going to be talking about gravitational waves, another really awesome signal from outer space that actually we do know what it's from. So this was theorized a long time ago by Einstein, and it's just so amazing that it finally came to fruition and we were able to detect it, not once, but twice, and I think even more. But so we'll go through gravitational waves next week, what they are, how they're detected, what it means for the future of the field, and what it means for Einstein's work. Don't forget to finish up your Hubble Tuning Fork Challenge. I posed this a few weeks ago when we did the galaxy classification. I posed a challenge that using Slooh telescopes to take an image of a variety of different types of galaxies, spirals and ellipticals, and their different shapes, and create your own Hubble Tuning Fork. And if you want to get those results over to me in the discussion boards, I will be sharing them on the show next week. So I know the Canary Islands telescopes have been offline for a while, and that might have made this really difficult. So certainly if you weren't able to do this because the Canary Islands telescopes are online, if I don't have any submissions, I will absolutely extend the challenge. But if you have been able to use the Canary telescopes to get them in, I've seen some really good galaxy missions, so hopefully those were yours and you were taking them down. If not, you have a week and make your own Hubble Tuning Fork. I will make a discussion board thread for it so you can all post your results there, and then we can share them next week while we talk about gravitational waves. All right, well, I hope you've enjoyed hearing about really weird signals, and I hope that I've left you thinking, wow, I wonder what that is. Have a great night and clear skies.